All right, let's go ahead and get started here with 3.4. We're going to use the derivative as a rate of change. And basically, anytime you see rate of change, or like you see rate of change of something, you're ultimately just going to end up dividing by time. So let's see what we can do here with it. Remember that the following ideas are all equivalent. Slope of a graph at a point, slope of the tangent to the curve at a point, rate of change at a point, derivative of a function at a point, limit of the difference quotient at a point. All right, all of these things are basically saying the same things. So definition here, the instantaneous rate of change of f with respect to x at x naught is the derivative f prime of x naught equals the limit as h goes to 0 of f of x plus f of x naught plus h minus f of x naught, all divided by h, provided this limit exists. Now, sometimes we don't say that word instantaneous, right? But, you know, it's also there quite a lot. They just mean the rate of change at that particular moment or position. All right, so let's look here. Diameter and area. Recall that the area of a circle is related to its diameter by the equation area equals pi r squared. And therefore, we can also have the radius. Remember, the radius is half the diameter. So we can take that and say that the area is equal to pi times the diameter divided by 2 squared, which is pi d squared over 4. And that gives us then the area of a circle as a function of the diameter. So this is the kind of thing where you change what something is a function of and kind of manipulate around until you get something like that. That is going to be important in what's coming up here shortly. So how fast does the area of a circle change with respect to the diameter when the diameter is 10 meters? So basically what we're saying is if we have a small circle and we take a teeny tiny change in the diameter, so let me do it this way. Here's the diameter, d, and then we have this teeny tiny little change, like a d, a tiny infinitesimal change in diameter. How much does that change the area? Well, when that occurs, what we ultimately do is add on this little ringed area right there in that little unit of time. Now, as the circle gets larger, right? So this is our new diameter here. Or maybe we should have made that in black. There's the diameter. And we have that same little teeny tiny change, a little infinitesimal change in diameter. And now we add that same thickness of a little super thin ring on here. We get a different area inside that ring that's been added on to the total area of our circle. And so the larger the circle gets, the larger this red ring around it is as it increases in size. And so therefore, the actual rate of change of the area, it varies as you go from different sizes of your circle. So if we take a look at this, we know that the area is a function of diameter, as we just found above, is pi d squared over 4. And so what we want to do is figure out what is dA dd. What is how much does, oops, I wrote dA dd. How much does the area change if we take a teeny tiny little nudge into a larger or smaller diameter? How much does that little teeny ring of area add on or subtract off depending on what we're making it larger or smaller? So as we do this, we can take the derivative of this first function here, right? Put a little star by it. And we take the derivative with respect to d. And so the pi over 4, that's just constant, so we leave it out front. And we take the derivative of d squared, which is just 2d, using our power rule. And therefore, dA dd is just pi d over 4. And so that's how quickly, or that's at least a function that tells us how quickly the area changes, or the rate at which the area changes as we change that diameter. We can then take this dA dd and evaluate it at d equals 10 meters, because that's what it asked us for. What is the, or how fast does the area of the circle change when the diameter is 10 meters? So we can do this. We can do pi, oops, I wrote 4 right here again. Sorry, that should be pi d over 2, because the 2 cancels with one of the 2's from the 4. So this is pi d over 2 evaluated at d equals 10 meters. And we plug this in and we get pi times 10 meters over 2. And that's just going to be equal to 5 pi meters. Okay? And that's really what we have there. So there you go. We've got our answer. 5 pi meters is our rate of change, dA dd, at d equals 10 meters. Okay? So it's just a matter of finding an equation that relates the two variables together, some sort of relation between them, and then plugging it in. If you looked at the relationship we have, it's pi d squared. That means if we start looking and start at a 0 diameter, we have a 0 area. So this is area in meters squared, and this is diameter in meters. This would be an x squared kind of relationship. It'd be a parabola like that. And what we're interested in then is what's occurring at 10 meters. At 10 meters, the slope of this tangent line is going to be the rate at which it changes. And of course, as you look at different places, the slopes of these different tangent lines means, just like when we were talking about the little teeny slivers of rings, they're all going to be different. So we're going to get a different rate of change at different sizes. All right, so here, when dealing with objects, we typically use the variable s and t. Excuse me. S is the distance or the position. Distance would be between two positions, and position would just be a single position. And this is for linear one-dimensional motion. So think of this as motion where we're like on a straight train track and we can only go forward and backwards on it. We can't move. A lot of other times you might see, instead of s, you'll see the variable x used for position or distance. And then t, pretty much always just used t for time. The symbol delta, this is the Greek letter delta, and it means change. And so what it is typically is final minus initial, or 1 minus 2. But anytime you see that, like if you see a delta S, it means S final minus S initial. So final position minus initial position. Delta T, T final minus T initial. Delta whatever. Delta, what would be something y'all might know? Delta T for temperature would be temperature final minus temperature initial. It's just always something like that. All right. So now the displacement of the object over the time interval from t to t plus delta t is delta S equals the function at t plus delta t, that's your final, and this is then your initial, minus f of t. Okay, so that's basically our displacement. If you remember vectors, it's a vector here. It has a direction. It points from the starting position to the final position. Now, keep in mind this delta S, anytime you see these delta somethings, it's one thing. So delta S for change in position or displacement, it's not delta times S. Okay, delta isn't isn't a variable. It's not delta times s, so you can't like cancel out deltas. Like if you had, delta x over delta t, you can't cancel out the deltas. All right, don't do something like that. I've seen students make that mistake. They're one thing, delta s. Delta s is sf minus si, which is what I wrote up here as well. Okay, so just keep that in mind. The average rate of change of the object over the time interval is velocity average, VAV, is equal to displacement over time. So it's a rate of change. And again, see, like I said earlier, anytime you see that rate of change of, you're going to be dividing by time. So this is going to equal delta S over delta T, which is going to be, our function final, f of t plus delta t, minus f of t all over t. And that should look, or over delta t. And that should look pretty familiar to you since we already had something like that, but with h's. F of x plus h, where now our delta t is our step instead of h. So if we had this in a graph form, we had some arbitrary graph going on, something like this. If this was t1 and this, then this distance here is delta t instead of h, then we essentially have a straight line between them like that, which would be their average, and then this would be delta t, and then over here, this would be, position initial, SI, which would be f of t1, and this would be over here, would be f of t1 plus delta t. Okay, and this is our our positions over on this axis, and then you'd have delta t, delta s like that, and that would be then delta s over delta t would be our slope, and essentially the slope of that graph is going to be our average velocity between 2 points like that. Now, obviously, we're not going to want to stay interested in this average velocity, but we'll look at it in a minute. So how do you find the average velocity at an exact time t? See, we want to get into that. What is this? What is the actual speed at a certain moment? Like how fast were you driving, if you were driving to the store, how fast were you driving exactly 3 minutes and 5 seconds into your trip, kind of a thing. And that's where we're going to want to do this. We're going to want to let delta t go to 0. So we're going to take that limit, let t go to 0. And when we do that, we get it here, we can define this as velocity, instantaneous velocity. So velocity at a moment is the derivative of position with respect to time. If a body's position at time t is s equals f of t, then the body's velocity at time t is velocity equals ds dt. So velocity is the rate of change of position. And then we can take the limit as delta t goes to 0, and this should look very much just like our original limits, right? F of x plus h minus f of x all over h thing with the limit as h goes to 0. So it should look very familiar to you at this point. So next, the velocity tells the speed and direction. It's a vector. So speed just tells you how fast you're going. Like if you are in your car and you look at your speedometer, it tells you something like, 45 miles an hour, but it doesn't tell you what direction you're going. You could be going around in a circle. You could be going north, south, east, west, northeast, northwest, something like that. We have no idea. So speed is what is called a scalar. Speed is a scalar. They scale numbers. And velocity, velocity is a vector. It's more like an arrow that points from one point to another. So it has basically velocity has speed, and it also has a direction. And if you take the magnitude of velocity, that's your speed. So your speedometer only tells you speed, but if you combine that with a compass, then now you can figure more out about it. You know what direction the person is going. So if you just tell me, I drove at 45 miles an hour. Well, I have, say I left my house and I drove 45 miles per hour for 1 hour. Well, I have no idea where you ended up. You could have ended up back at your house if you'd just gone in a big circle or a bunch of small circles. You could have gone north, south, east, west, whatever. But if you say, I left my house and I traveled 45 miles per hour for 1 hour due north, now suddenly I can figure out exactly where you ended up. So the vectors, all right, the vectors versus the scalars, they're just a little different there. Okay, if you have any more questions about those, if you take physics or something, you'll learn about them there. But if you have any other questions, just let me know. I can give more details about vectors versus scalars. Okay? So next, this is don't be a D3 S dt3, d cubed S dt cubed. This is actually what is called, in physics terms, it's called jerk. Jerk is the rate of change of acceleration. One of the nice things about general physics is you rarely, if ever, talk about this. We always do stuff where we have a constant acceleration. Okay, so this is the rate of change of acceleration, and it's called jerk. So acceleration is the derivative of velocity with respect to time. If a body's position at time t is s equals f of t, then the body's acceleration is the second derivative, all right, of position with respect to time. That's why you might see things with accelerations. If you're in physics class, it's meters per second squared. We have 2 times down there, okay? What this is really saying is it's a meter per second, that's your velocity, per second, all right? It's the rate of change of velocity. You're changing 5 meters per second every second. So whenever you see an acceleration, it's telling you how much the speed changes per unit time, or typically per second. Jerk is the derivative of acceleration with respect to time. So it'd be the third derivative of a change in position, okay? So this is the rate of change of acceleration. It would be meters per second cubed, which would be meters per second squared, the acceleration per second, okay? Acceleration measures how quickly a body picks up or loses speed. Not necessarily. It can also measure how quickly, actually it should say it's a measure of how quickly something changes velocity, okay? Because you can also, just by turning, have an acceleration even if your speed stays the same, okay? So let's change that to velocity. Okay? A sudden change in acceleration is called a jerk, or just really any change in acceleration is a jerk. All right, right here we have a velocity versus time graph. Previously we just looked at a position versus time graph. If we look here, this is pretty much all mapped out for you, where you can look and see, like it asks you here, when does the particle move forward? Well, the moving forward stuff is going to be any time that you have a positive velocity. So that's going to be anything in this upper half of the graph where the velocities are positive. So that's going to be everywhere here in this blue and everywhere here in this blue. That's where you are moving forward. Where are you moving backwards? Well, that's going to be everywhere you have a negative speed or a negative velocity, and that's going to be down in the lower half of the graph. Okay, so all the answers to these are pretty much written on here for you. Like, when does the particle speed up? Well, that's going to be when the velocity is increasing. And so that's along this line right here. The velocity is increasing. And that's also right here. The velocity is increasing, right? The velocity here is less than the velocity here. So as time goes forward, time moves in this direction. We were here at this speed, and now we're over here at this speed. So we have increased in speed. When does it slow down? Well, here we have a faster speed than here. As we move forward in time, we're going down in speed, so that's slowing down. So anytime like that, okay? So take a look through these and see if you can, figure these out. Especially pay attention here to the speeds up and slows down here. Because when we're talking about speeding up, we're not talking about necessarily a positive slope, but rather getting further and further away from a zero velocity, which is this whole axis right here. So right here, we're technically speeding up. We're getting faster and faster. We're just getting faster and faster in the negative direction instead of in the positive direction, okay? So that's really what matters there. And here we're slowing down. We're getting slower and slower, from going in the negative direction. So take a look through those and see if you can work out all of that stuff. And I'll clean this graph up for you here, okay? Next, is gravity a jerk? So remember, jerk was rate of change of position. So we know pretty well that near Earth's surface, the position of a falling object is told by this equation. All right, this is from Galileo. A lot of people think Newton gave us this, but it was actually Galileo. S is the distance you have fallen, and it equals 1/2 gt squared, assuming it is dropped from rest. In other words, you didn't throw it downwards, you had it in your hand or something, and you just let go of it and let it fall. The first time derivative of this will give us velocity, which is ds dt. And so as we take the derivative with respect to time, we get 1/2 g. Those are constants, all right? The time is the thing that's changing, and that becomes 2t. And so this just becomes gt. To get acceleration, we take one more time derivative. So this is d2s dt squared, taking another derivative. So we take a derivative of this. Well, the derivative of t is just 1. So this is just a g. Now it's a constant. And then the last thing, jerk as a function of time, would be d cubed s dt cubed. And this is the derivative of a constant. That's just 0. So what we're basically showing here is that near Earth's surface, the acceleration due to gravity is always the same. And here are the values that are most commonly used for g as a constant near Earth's surface. 32 feet per second squared, which is 32 feet per second, or 9.8 meters per second squared, or 9.8 meters per second. So if you look at this, you could say I dropped something from the top of a high building. How fast is it going after 1 second? Well, after 1 second, it's going to pick up 32 feet per second, or it's going to pick up 9.8 meters per second. So after 1 second, you can either say it's going 32 feet per second, or you can say it'll be going 9.8 meters per second. After 2 seconds, it's going to be going 64 feet per second, or 19.6 meters per second. So every second that goes by, you're going to add on, depending on which units you're working in, feet per second or meters per second, you're going to add on that amount of speed. All right, so here, let's take a look at this ball getting dropped. The figure to the right shows a free fall of a heavy ball bearing released from rest at time t equals 0 seconds. How many meters does the ball fall in the first 3 seconds? We can see this from the picture. It's showing us right there that it fell 45 meters, or just about that. It might be slightly before it, but let's see if we can calculate that. Now remember, we used s as a function of t is 1/2 gt squared. All right, this is done in meters, so we'll use the 9.8 meters per second. So for part A, we get s equals 1/2 gt squared. We're doing 3 seconds, so this is s as a function of 3 seconds. As we plug in 3 seconds, this is 1/2 g, which is 9.8 meters per second squared, times time, here in this case, which is 3 seconds squared. So we get 1/2 times 9.8 meters per second squared times 9 seconds squared. So our second squareds will cancel out right there, and we're left with 9 times 9.8 meters, and then divided by 2. So ultimately, we get 44.1 meters. All right, that's our position after 3 seconds. It's fallen that far. And so that's about what it is on our little graph over there. The next is, what is the velocity? What is its velocity, speed, and acceleration when t equals 3? Well, the first one, or the last one, should be the easiest. So first off, what is its acceleration? Well, the acceleration near Earth's surface is a constant, so that means 9.8 meters per second. But let's see if we can solve that. Okay, so starting with velocity. Velocity is ds dt, and we just did that derivative on the previous page and got g times t. All right, so that means velocity is after 3 seconds, is going to be 9.8 meters per second squared times 3 seconds. And that gives us equal to, and in this case, this is a negative 9.8 meters per second squared because it's actually, we're worried about velocity here, which includes direction, and it's falling downward. So we put a negative there, and this becomes negative 29.4 meters per second. There you go. The second cancels with one of those seconds. You're left with meters per second. Negative 29.4 meters per second. For the speed, it should be pretty simple here. Remember, speed is the magnitude or the absolute value of velocity, which means it's the absolute value of negative 29.4 meters per second, which is just 29.4 meters per second. So there's your speed. And now acceleration is the time derivative of velocity, which is the second time derivative of position, which is just the time derivative of gt, which is just g, which is just a constant, which is just negative 9.8 meters per second squared. There you go. In fact, I might go back here and add negatives right there. These are actually negative values, okay? Those are my little negative signs. All right, so next, I'm going to leave this one for you to try, and I'll work it out in the notes so that you can see it. And it continues on here with some part C and D. So give this a try, and I'll work this all out in the notes. And if you have any questions, you can ask me. Same thing for this one. Again, leave you something to try, and I'll work it out in the notes so you can look at it. And then I think that's pretty much the rest of these are just some practice things that I'm going to try leaving for you. We can work them out in class if you want. Otherwise, just try working on these and then take a look at the notes and see if yours matches what I came up with. It kind of help you show you how well you're understanding it. All right, that's it for this video. Thank you.